Lesson 5-1, solving polynomial equations by graphing. Ooh, by graphing, that means I'm going to pull out Desmos. We're going to be using Desmos a lot today. All right, so we're still in polynomials, and a lot of this lesson has to do with where do two polynomials cross each other, and what would that mean, say, in terms of like heights of roller coaster in this case, or how could you use to solve Spartan puzzle or this pool puzzle here. And so yeah, so we'll go through all the examples and highlighted ones, just like normal here. And so example one, solve polynomial equation by graphing. Using a graphic calculator to solve, we got y equals x to the 4 plus 3x squared minus 5 equals negative 4x to the 3 by graphing. So I think I got those right here. Yeah. All right, so that is that. All right, so we got the red one and the blue one, and where are those equal to each other? So if you graph these, that's to say, where does the red line and the blue line cross, right? Where does the red and blue cross, right? And you could figure this out by graphing. Let's see if I click this point. Okay, it looks like the x value is 0.84, right? And there's a y value of negative 2.37. Now, if you were interested in just the x value, like what's the x value where they cross, then there's an interesting way you could solve this, which is you could set these two equations equal to each other. You could get it set equal to 0 by subtracting one side over, right? So in this case, if I add the 4x to the 3 over, right, by setting the red equal to the blue, right, then it looks exactly like the green. But this would all be equal to 0. So if I say this is equal to 0, here, I'll write this on a paper, right, just in case anybody's lost on that, but what that means. That's, right. If you know what I'm talking about, you can skip ahead a minute, but if you're totally lost, then here it goes like this. Right, we got y equals x to the 4 plus 3x squared minus 5, right? And a separate equation, y equals negative 4x to the 3. Well, if I set these equal to each other, right, then what I'm really interested in is where is x to the 4 plus 3x squared minus 5 equal to negative 4x to the 3, right? Now, I could solve for x like this, right? Um, how can I do that? Well, I'm going to add 4x to the 3 over, right? And then over here plus 4x to the 3. Okay, and that gives me this expression, x to the 4 plus 4x to the 3 plus 3x squared minus 5 is now equal to 0. Well, if I treat this as a new function, I could call this like h of x or whatever, right, is equal to 0. I can say, well, where does this function cross the x-axis? Where is it equal to 0? Because it would give me the exact same x value. Let me show you guys that that is true on Desmos. And so now we're back to here. Okay, so we got the same ones going on. So, hey, this is the green one that I just came up with. So is it the same x value? So these two, the red and the blue cross it where x is 0.84. Where does this green one cross the x-axis? Right here. Also at 0.84. It's the exact same x value. Exact same x value. See, is there another place where the red and blue cross? Yeah, it's like way, way up here. Now this other one's kind of hard to tell because these. Okay. Oh, you know what? You know, my other class did show me though, is that if you click this little wrench tool, you can change this. Let's see, what should I scale this to? Maybe like 100 or something. Let's change the Y from like, let's go negative 100 to positive 100. Right? It should frame this a little better. All right. See if that did it. Okay. Yeah, a little bit maybe. Okay. So where did the red and the blue cross? Well, it's somewhere in here. It's kind of hard to tell, right? But I can know exactly where they cross. It should be right here at negative 3.21. Let me see if that's pretty close. Negative 3.21. Does it give me a dot somewhere up here? Yeah, okay. Kind of hard to tell. But somewhere about, oh, there it is. It honed in on it and locked in on it. Yep, that's it. That's the point right there. So where the x value is negative 3.21. All right, so there you go. And a lot of these puzzles in this lesson are pretty much just like that. Okay? Now, some of these are word puzzles, so we have to think a bit more abstract, like, how can I take this real life type scenario and convert this into math, right? So that's exactly what we had for example two. Got animals for an exhibit with 6 or fewer emperor penguins. And so we've got an aquarium going on. The pool must have a depth of at least 4 feet and a volume of at least 1620 gallons, or about 217 cubic feet per penguin. Right? Now, if you take the ratio here, you can figure out how many gallons are in a cubic foot. 1620 over 217. This would be gallons per cubic foot. Take a guess. Take a guess. Like if you had a cubic foot, if you look at a floor tile, it's 1 foot by 1 foot, and then you expand that to cubes, so it's 1 by 1 by 1. How many gallons do you think it would take to fill that? And wildly enough, it ends up being almost 7.5 gallons. Yeah, I remember learning that in college, and it's like, what, really? It would take like more than 7 gallons to fill a cubic foot? But yeah, that's apparently true. So, right, so that's consistent with something I've seen many years ago. Um, if a zoo emperor has 5 emperor penguins, what should the dimensions of the pool be to meet the minimum requirements? Looks like they have this other requirement if they're looking for certain ratios of dimensions. So if they call height 2x, they want this width to be 2x plus 3, so 3 feet more, right? And then this length to be 5x minus 2 for whatever reason. Right, so what you can do is set up volume is equal to length times width times height. So you can multiply these 3 dimensions. So 2x times 2x plus 3 times 5x minus 2, what's they do here? And they want that to have, well, okay, what do we say? 5 penguins, and they're doing everything in cubic feet. So I'm going to use the 217 number, 217. That's where they're getting the 1085. See right here, they have 1085, right? So, so we want these dimensions to be at least 1085 when you multiply everything out. So I think that's the next Desmos graph I have right here. Let's see, is that? Yeah, that's it. Right. Yeah, I already truncated this axis. I already clicked on this wrench tool and right. So you see a blue line here at 1085. That's sort of like the minimum volume we have to have. Okay, and then in red, I just multiplied the dimensions of the box. Now, could you, if you want to, could you like FOIL this whole red equation out, make something that looks like a polynomial in standard form? Yeah, you could, but it wouldn't actually change the graph or the answer to this. So I went ahead and just left it so you can see exactly where that comes from. Right? Now, just like the last example, if you take the difference between these two, say what's the red curve minus the blue curve, it'll give you this green curve. And where the green curve crosses the x-axis, that's exactly where the red line crosses the blue line. You can see here anyway, because Desmos gives it to me. It's where x is 3.5 feet. X is 3.5. Okay, now how about if I go down here to get the exact same number? And yeah, it's exactly 3.5 feet. Right? So it should be x is where x is 3.5. There's a little more to this because the actual question is what's the dimensions? Okay, so 2 times, well, I got 2x. So where the x goes, I'll put 3.5. They will call that a height. The width is 2 times 3.5 plus 3, and the length is 5x minus 2, so it's 5, 3.5 minus 2. So here, I'm going to go to the calculator. Well, this would be 7, that'd be feet, right? And then this would be 3 feet more than that, so that's got to be 10 feet. Right? And what is 5, 3.5 minus 2? Right, that's going to be 15.5 feet. Okay. So these are the actual dimensions you would want on that aquarium. Okay. Now go back and make sure that it does pass all the conditions. They said it has to have a depth of at least 4 feet. And here I have a depth of 7 feet. Yeah, okay, so that works. Okay. So this is matching all the requirements. And so yeah, you want so minimum volume for each of your penguins. But there's maybe also an economic constraint, like if you made this the size of like Michigan or something crazy, like, well, okay, that's too expensive to upkeep. Right? Okay, so this is a good trade-off on our fund. Right. And that's really just the 2 examples that your book has. Right, so let's go through the rest of these then. Right, got 2 very mathematical examples. Use graph calculators, solve each by graphing. If necessary, round to the nearest hundred. Now, you guys know that you totally can make an XY table for each of these, right? So if I wanted to, I can say X, Y. Okay. I get to start plugging values back 0, 1, 2. I can plug this in my calculator. Here, I'm going to take a minute to remind you guys how to do this. If you want to skip this part of the video, you can skip ahead. Right? But if you want to see this again, so I'm going to do 2/3, and then where X goes, I'm going to put answer. Oops, answer to the power of 3 in this case, plus, and then X, I'll do answer to the power of 2, and then minus 5 times answer. Right? Now, Here, maybe I'll just graph that part, right? Maybe I'll say y equals that, right? Just see what happens. Now, if I plug in 0, what do I get? Oh, okay. Well, okay. Of course, if I plug in 0, I get 0 because each of this has an x term in it. What if I plug in 1? Right, I get negative 3.33. What if I plug in 2? Let's see. Gives me negative 0.67. It's okay. So you can make as many points as you want and then make a graph like that. Or you can throw this into Defnos, which, again, done ahead of time. Right, so that looks like this. Okay. So on the left side of the equation, they have what I wrote in red. I said y equals that. On the right side, they have just -9. So I said y equals that. Right, so if you look at the graphs, you just focus on the red and the blue. Another way of saying this is where does the red cross the blue? Right? And it looks like the answer is right here where x is negative 4.5. Yeah, so x is negative 4.5. Uh, or just like I did before, you could add over 9 and set the whole thing equal to 0 and make one equation. And that's exactly what the green one says. It's all, you see, I just added over 9, right? So where's this green one equal to 0? It should be the exact same solution. So I'm looking for 4.5. And let's see here. Oh, you know what? You know what? Let me zoom in a little closer because this was not exactly, okay, never mind. Sorry, it's not negative 4.5. That's this point here. That's not what I want. Here's where the red crosses the blue. It's at negative 4.12 about, negative 4.12. And so is that also where the green crosses the x-axis? Negative 4.12. Yeah, so it's that point right there, right there. That's it. X is negative 4.12. That's what I'm looking for. Let's try another one. How about number 4 here? So here, I'll go ahead and list out the equations that I would put in Desmos for number 4. So we've got x to the 6 minus 15 is equal to 5x to the 4 minus x squared. So I'll graph both of these in Desmos. One of these will be red, one will be blue. And where does the red cross the blue? Well, another way to say that is I can make a third equation. I could just subtract one equation from the other. So let's say I have this and I subtract off this equation. So let me show you guys where I'm getting this from. Right. So if I do, if I say one is equal to the other, right? So I'm setting them equal to each other. Then that would be x to the 6 minus 15 equals 5x to the 4 minus x squared. Right? Right. So then if that's true, if this equation is equal to this equation, okay, that's why I'm subtracting over. Because if I subtract it over, x6 minus 5x4, okay, then minus the negative would be plus x squared, and then minus 15. Okay? Then I can get it set equal to 0. I could just say, well, where does this third equation simply cross the x-axis? It's going to be the same answer. And I'll show you guys that that's also true. Where these two lines cross, this will be red and blue in Desmos, this green equation will cross the x-axis, and it'll be the exact same answer. Let's see, that's, I think this right here, I think that's the same equations, right? Yeah, it looks like the same equations. Boom, boom. Okay. Now, where does the red cross the blue? Okay, that's way up here. In fact, that's so far up, I should probably truncate this axis a little bit. Let's see if I can do that. Let me change y to, uh, let's go from negative 20 to, let's say, positive 100. Okay, see, does that frame it a little better? Did that even do anything? Yeah, okay, whatever. I'm kind of there anyway. Right. It's kind of hard to tell, but it looks like somewhere. Right. See if I can get kind of an estimate. Um, well, you know what? You know what I know is definitely going to work better anyway. Is it's just wherever the green crosses the x-axis, which looks like right here. So this would be about 2.3, and to here at negative 2.3. Okay, so 2.3, negative 2.3. Now, can I confirm that up here? Okay, where the red crosses the blue. Okay, it's somewhere right in here. Hard to tell. Let's see if it locks in on it. Okay, no, still gotta go up a little bit, a little bit. Let's see if it locks in on it. At 2 point, I think it's right. Just give me a little gray dot right there. I think that's it. I think that's it. Yeah, I see a little gray dot right here. Yep, it's the exact same x values at 2.3 and negative 2.3. All right, so there's another winner right there. We got that. Right, number 7, shipping. A shipping company will ship a package for $7.50 when the volume is no more than 15,000 cubic centimeters. Grace needs to ship a package that's 3x minus 5 centimeters long, 2x centimeters wide, and x plus 20 centimeters tall. Write a polynomial to represent the situation if she plans to spend a maximum of $7.50. Okay. So here I can draw this package out. Let's say it needs to be, okay, left, draw like a 3D box. Right, and we'll just label all those dimensions. So there's some dimension there, and some dimension there. Right, so let's fix that. Let's see, 3x minus 5 centimeters long, and 2x centimeters wide, and x plus 20 centimeters tall. Okay, so you just pick each dimension and just write one of those. Right, so I could say the volume as a function of x, if you write it that way, could just be all those multiplied. 3x minus 5, 2x, x plus 20. Okay. Now, I do want the volume to be less than or equal to 15,000 cubic centimeters. Okay. So what I can do is set these equal to each other and then therefore subtract over the volume and get it set equal to 0, just like I've been doing all along. Right? So I could say if 3x minus 5, 2x, x plus 20. Okay. How about this? It has to be less than or equal to 15,000 because this is more of an inequality type, right? And x would be in centimeters, so everything's going to be in centimeters, cubic centimeters. Right? So I could subtract over the 15,000. 3x minus 5, 2x, x plus 20, minus 15,000. And that has to be less than or equal to 0. Right? Okay, could you FOIL all this out and expand this to make a proper polynomial? Yeah, you totally could, right? But it wouldn't actually change the answer. Right, so here's what this looks like. Right, the dimensions of the box are in red. Now, of course, X could be anything. You can have a small box, a big box, right? But the sort of economic limitation is this blue line, right? The box would be no bigger than this. So where those two lines cross, okay, it looks like X would be equal to 10 in that case. Now, to get the actual dimensions, you have to plug that back into the original statement. So I will do that on paper. I'll go back and figure out what are the actual dimensions. So where X is 10. Right, but look what I did in green is I subtracted over the 15,000. So this green line should cross the x-axis at exactly the same place. Look at that. It is the same place. It's where x is equal to 10. X is equal to 10. All right, so I will just plug in, I will just plug in 10 for x. Ooh. Yeah, so let's just plug in 10 for x here and figure out what are the dimensions. Right, so um, so 2x, 2 times 10 would be 20. Right? These are all in centimeters. Right? If I do 3x minus 5, and then I'm just plugging in 10 for x, that'd be 30 minus 5 is 25 centimeters. And the height would be x plus 20. So that'd be 10 plus 20 equals 30 centimeters. Right? Just like that. All I did was I took each of the length, width, and height, just plug in 10 where the x goes, because that's where we saw the graph. Right? So I could say this, the maximum dimensions to meet all the requirements, right, to fit this type shape from the beginning, but also be able to go through the mail for $7.50, okay, is got 20 centimeters by 25 centimeters by 30 centimeters. Right? So that's the biggest package that she can send. So there you go. All right, next one, garden. A rectangular garden is 12 by 16. Okay, that's just the garden itself. But there is a surrounding border of mulch that is uniform with X, and the maximum area for the garden plus the mulch border is 285 square feet. Write a polynomial to represent the situation, solve a system of equations, and what are the dimensions of the garden plus border? All right, so I'll find it out right here. All right, so All right. The maximum area, okay. I could say this. I could say that the width is equal to 16 plus 2x because here's the 16. And there's also width of x on the right side, but also width of x on the left side. So that's 16 plus x plus x. That's where we're getting at. And there's a length. Well, it looks like the height of the page. I'll just call it length. Could be same idea. Okay, so 12 feet for the garden itself, plus this x here, plus this x down here. So that's like this, right, like that. Right now, the area is equal to width times length. So I can just feed each of these expressions in. So here's for width, right there. Here's for length, right there. Pop this in. So the area, say, is a function of x. You can think of it that way. It could be 16 plus 2x, and then 12 plus 2x. Right? I've been saying all along you could FOIL these out if you wanted to. This one's a pretty straightforward FOIL, so I'll do this one for you guys. So first outside, inside, last. So area as a function of x, if you want or standard looking polynomial. What is 16 times 12? It's 192 plus the 32x, then plus 24x. That's outside, inside. And then 2x, that's 4x squared. Okay? So area is a function of x. Well, normally you put the higher powers of x in front, so I'll go ahead and do that. 4x squared plus, then I can combine outside, inside, 32 and 24. That's 56x, and then I got 192, right? So that's area as a function of x. Okay, so we got that polynomial situation. Okay, you know what? All right, that is the area for any garden. Right? But there is another condition here, which is that A max is equal to 285. Right? Yeah, everything's in terms of feet, so area would be in square feet. Okay? And so what I could do is I could bring these two ideas together, right? And this will look a lot like that shipping package example that we just did. Right, where this will be an inequality. So the 4x squared plus 56x plus 192 has to be less than or equal to 285. This would be in square feet, x would be in feet. Right? So I could plug this into Desmos and just figure out where these two graphs cross, right? So this graph and this graph, where do they cross, right? Or if I wanted to, I could subtract this over and say, where does it all equal zero? Or well, less than or equal to zero, I suppose. 4x squared plus 56x. See if I subtract 285, what's 192 minus 285? Be minus 93. That would be, let's see, less than or equal to 0. Okay, something like that. All right, so I plugged in the equations here. Okay, so the general equation is in red, right? And I did not expand this out into standard form, but if I had, the graph itself wouldn't actually change. Right? The limitation here is this blue, and then if you subtract one from the other, you get the green. And so where's the red cross the blue? It looks like where x is equal to 1.5, or same thing is where the green crossed the x-axis, which is, of course, the same value. X is 1.5. Right, so I'm looking for x to be 1.5 would establish that Lindley situation. Okay, and is it what are the dimensions of the garden plus the border? Right, so x is 1.5, I guess feet. That would be the location where that would happen. And so the length, remember, was 16 plus 2x, and the width was is that what I call those? No, I was calling this width and this length. Okay, you guys get the idea. Right, width, length, 12 plus 2x. Right, so just where the x goes, just put 1.5. Well, that would be like 16 plus 3 here, and this would be 12 plus 3, because 2 times 1.5 is 3. Right? So dimensions are, this is 19 feet by 15 feet. So there you go. Right. All right, roller coasters. On a racing roller coaster, you got two trains start at the same time and race to see which returns to the station first. One roller coaster, at um, the height of the train on a blue track can be modeled by this function. The height of the train on a green track can be modeled by this function, where x is the time in seconds for the first 35 seconds of the ride. Assume that both trains start at a height of 0 feet, right? Which you could also get from the equations anyway. Do you guys notice that every single term in both equations has an x in it, right? An x and an x squared, and x. Okay, so right, there's no like plus a constant at the end, right? So your natural assumption would be that at time zero, the height is zero. Right? If they wanted this to be anything else, like they said, oh, actually, one train starts at like 5 feet up. All they have to do is say plus five, right? And then at time zero, the train would be starting at plus five. Right? So that's how you can fix that. So what equation would determine the times when the blue and green trains are at the same height? Well, that would just be one equation minus the other equation, and then you'd set that equal to zero. Yeah, so you do that. Using graph calculator, yeah, I have that queued up in Desmos, so I'll do that for you guys, and then, well, determine, oh, okay, yeah, and then there's a question C, but let's start with questions A and B here, right? Right, so A and B, right now, I know they have a blue and a green train, so my colors are a little different. I have a red and a blue. You guys get the idea. So the red and the blue are the two uh, equations. So height is a function of time, right? They say it's just for the first 35 seconds. So I guess at 35 seconds, you can cut it off. Where does this go to? Okay, so right there. Yeah, okay. But if you subtract one equation from the other, then where they would be the same height is also where this third equation is equal to zero. And it looks like that happens. Okay, at time zero, well, at time zero, they should, oh, here we go. They should both be at height zero. So 0, 0, they should cross there. It's 0, 0. Also, it looks like at 9.6 seconds, they would have the same height. And also at 26 seconds, they have the same height as each other. Okay? If you want to know what that height is, just take that time, in this case 26 seconds, plug it into either the red or the blue, and it'll tell you exactly what that height is. Like that. Right now, this third one I just want to go over with you guys verbally. It says, write an equation for determine the times um, in which the blue train modeled by FX is a height of 150 feet. Use a calculator to solve the equation. So what you do is you take the blue equation, which is this first one. You could set it equal to 150 and then solve that. Right? Or you could subtract over 150. So take this minus 150 and set that equal to zero. All right, so you guys get the idea. All right, number 20. All right, last one I'll do with you guys here. During practice, a player kicks a ball from the ground with initial velocity of 32 feet per second. The polynomial f of x equals negative 16x squared plus 32x models the height of the ball where x represents time in seconds. Now, I know this is already here. Here. This is something that you guys have seen over and over and over. This situation has popped up in a lot of past lessons, which is height as a function of time. As long as you're in Earth gravity, then the number in front of the x squared is always going to be negative 16. That refers to feet per second squared. Okay? Because Earth gravity is 32 feet per second squared downward. And if you take my physics class, you'll see why. If you take half that value, you can make an equation with that. If you were working in the metric system, so if you're working in meters, here I got a meter stick here, then gravity would be very close to 10 meters per second squared, more precisely 9.8. And this number would not be negative 16. It would be either negative 5 or negative 4.9, depending on your precision. Right, but we're in feet in seconds. So you guys have seen this before. All right, so now we have a second player kicking a ball in distance c feet off the ground. Initial velocity 27 feet per second, which is given by this polynomial. So height as a function of time is negative 16x squared plus 27x plus c. Right? Or again, x is the number of seconds after you kick the ball. If the balls are at the same height after 1.2 seconds, from what height did the player kick the second player kick the ball? So it's basically what is c equal to? So what is c? All right, so what I did here is I graphed both equations. All right, so I got the red and I got the blue. But remember, this blue one here is incomplete, right? Because I need some kind of plus C. Actually, you know what, before I dive into the equations, I should really show you guys a picture of what's going on. So let me get what's going on here. Get a picture. Right. So there's uh here, let's say the first ball is like at ground level. And the second ball as well, it's up here elevated at some height plus C. And we don't know what that height is, but I'll just call it C. Right, C. Right, but we don't know what C is. Okay? Right, this first player is going to kick a ball pretty much straight up, right? And it's going to maybe go way up and then come back down. Right. The second player kicks the ball, right? Not as fast, and I know it's not as fast because I see it in the equation. The first player kicks this at 32 feet per second. The second player, well, it's only 27 feet per second, so it's not as fast. So maybe it's like V1, this is V2, right? V for velocity, something like that. Okay, just like this. Now, does the second player's ball go higher than the first player's ball or not as high? Well, it depends on what the C is. So right now it's kind of an ambiguous situation. I don't know that yet. Okay. We can sort of figure that out once we know this last detail. It says the balls are at the same height at the 1.2 second mark. Okay, so let's say that's, for example, like right here. I don't know, maybe, right? Maybe not. I'm just giving a picture example. So if they're at the same height at this time, then at that point there is enough information to determine exactly what this initial height C had to have been. All right. So now that you guys have a better picture, let's flip back over to the equations. See, was it this? Nope. Okay, hold on. I got a lot of equations open. I gotta dig through and find this. Is it this one? Yeah, let me pause this video and find those equations. Okay, yeah, it is these right here. All right, so here's the red and the blue. Now keep in mind this last one should have a plus C on it. Right? So I could I guess there's different ways to tackle this, but the most straightforward way would be to subtract one equation from the other, right? And then there's some mystery plus C, and then get this all set equal to 0. Now, what I did was a little bit of trial by error. Now, I have the answer right here. The answer turns out to be 6 feet, but how did I get that? Right, so if I see delete this out of here, right? It's plus something, I don't know, right? Suppose it's plus 0, right? Like, there's nothing on the end. Then I could say, well, the only time they would have been at the same height for sure is when they were both kicked initially, because they were both kicked at the same time. At time 0, they both start on the ground at 0, right? Right, so that would be true, right? But what if you elevated one ball by 1 foot? Right? And this would be the second ball, right? So like if I have a plus 1 here and I subtract that over, and so I do the blue equation minus the red equation, right? That's why I have a plus 1. Otherwise, if I subtract it the other way, I'd have to have a minus 1. Let's do a plus 1 here. Then the balls would end up having the same height at 0.2 seconds. Oh, well, that's interesting. What if I raise the height a little more to 2 seconds? What if 3 seconds, 4 seconds? How about 5 seconds? Well, or sorry, not seconds, feet. 5 feet. 1, 2, 3, 4, 5 feet. Well, if one ball had been elevated by 5 feet, then they would have had the same height at exactly 1 second after kicking. Now, your textbook says after 1.2 seconds, so I can do 6, and then bam, there you go. They're at the exact same height at the 1.2 second mark. So I know that the second ball was elevated initially 6 feet up. So this would have to be 6 feet, right? So there's a trial and error way of solving that, right? Some more formula way you can do that too, but there you go. Here. So a trial and error way. All right, so there you go. There is a tour of lesson 5-1.